So, welcome back, or welcome. Depends on if you've been in my talk before or not. This talk actually got finished like during the SharkFest', so kind of fun to do. It's like my talks usually get always done like in the last 5 minutes before I do it, so I'm lazy, as I already told you. We'll be on a little adventure here because I wanted to do something about TCP that you probably have not seen or maybe have seen but not understood. It's not about sequence numbers, egg numbers and all that in the basic sense, but it's going to be more like the advanced stuff. Okay, so I don't know if you have ever read an RFC. I do that all the time because if you're coding and trying to dissect something, you need to read the RFC. It doesn't necessarily mean that what's in the RFC is what you're going to see in the packets, because people do crazy stuff when they think they read the RFC, or when they did but don't care about what the RFC says. So if you want to try reading something crazy, try following DNS packets. It gets my tool crashing all the time because people just do crazy stuff with it. So now we're at TCP Stuff. Once again, my name is Jasper Bongertz. I work for Airbus Defense and Space. So our slogan is "We make it fly." And well, the defense and space is basically the fighter airplanes and satellite construction stuff. And, yeah, they also use TCP sometimes. I had a funny thing when I was looking at the RFCs, and you've probably all seen this. And as a little wake-up call, I want you to find me one thing that is quite unusual in this. There's one thing where I was like, wait a minute, this can't be right. Can anyone see it? It's from 761, so it's even before 793. There's one thing that is something you don't see anymore today. Which one? EOL. Have you seen the EOL flag before? This one? You know, the funny thing was I was sitting there like, I had never seen the EOL flag, but wait a minute, there's still the 6 flags, so which one isn't there? Which one is missing? Push is missing. Yeah, so EOL, meaning end of letter, was the original name for the push flag. So it got replaced in the next RFC, which is in fact 793. And they just relabeled it to push instead of end of letter, because pushing means, I hope you know all this, pushing means that this needs to be processed right away on both sides. I had a talk to somebody about, well, does it mean you only need to push it out fast, or does it also mean you need to process it fast on the receiving side? I found the paragraph that says, yes, you also need to process it fast on the receiving side. So the trace that this guy had, and I think it was Simon, there was an error condition in there where even though there was a push flag in there, it wasn't processed fast. It was like 200 milliseconds or something. So that was not working correctly in TCP state. So this is just a little fun with when you read old RFCs, and you can even go before the 761. There are documents you can still find on the internet about TCP that predate the RFCs. And if you read the early RFCs, they're always like, yeah, we have stuff that is written somewhere else, but we can't give you a number because it's not an RFC yet, so look up there. I won't go into that much more. I want to go into the current thing. So, selective acknowledgements. Who knows what a selective acknowledgement is? Like, let me say 10 people? Really? The rest doesn't? Who's been in Laura's class? Okay, I think she probably talked about sex, did she? Yeah. Okay, you forgot about it already? Really? Okay, I have to talk to her. Maybe she's speaking too fast. Good. What does it mean, selective acknowledgements? Selective acknowledgements basically mean that you have a way of telling the sender that something is missing and that you've got something else. You can see here we have a stack edge block here, left and right edge, and you can see it's higher than the edge number. That's the usual key that this is a selective acknowledgement. And the ACK number, as you may have seen in my talk last year, is always the number that tells you up to what point the whole data is intact on the receiving side. There's no gaps before that number. There can be, but there can be gaps after that number. And if there are, usually you get a acknowledge for the last sequence number that was received. But with selective acknowledgement, the receiver can also let you know, by the way, this is what I got in total, but I also have these blocks already received with gaps between them. Or at least with a gap between the block and the previous complete block. So I made a little graph to make it easier. So this is complete. Everything is up to this number has been received. Then there's the gap. There were like 2,000 bytes lost, which is not a 1460 number, but I wanted to make it easier. Then I continue at 8,000, and I have 1,000 bytes received, so I tell the sender, well, I got all of it up to that point. Here's the gap. This is what I'm missing. I need this missing part again. I got this. You don't need to send this, but there's something else missing, and I got this. So with selective acknowledgements, you can tell quite exactly what you still need from the sender. So if you get data after a missing segment, you can tell them, like, I got this, I got this, I got this. And the edges are always like trying to cover the whole blocks that were received. So if I get a lot of data after a missing block or after a missing segment, they will be adjusted all the time. So if you see a lot of SACs or selective acknowledgement blocks, they will be expanding very often. So, with the demo, I got a couple of traces. We're going to look at them and try to make some sense of them. Starting easy. So, in the beginning, nothing bad is happening. So let's go down. As you can see, I use color filters very rarely. I use them only when it matters, and I don't care about this is HTTP, this is DNS, let's make it blue, let's make it green stuff. It's too annoying. By the way, if you need my color filters, if you want them, I've put them on my own cloud. You can get the download link, or if you follow me on Twitter already, I posted it somewhere, so you can find it there. There we got a previous segment not captured. That basically means, we have packet loss. Previous segment not captured, by the way, if you haven't noticed already, this is the new or newer message Wireshark puts out when something is missing. In previous versions, up to 1.10, I think, or 1.8, it said previous segment lost. Previous segment not captured sounds a little less exciting, but this is because we wanted, or the Wireshark developers wanted to include the fact that just because the segment is not in the capture, it doesn't mean it wasn't on the wire. It could have been that just your capture wasn't good enough. You weren't capturing fast enough. So if you have packet drops, like packets that you didn't get because you weren't fast enough, that is like not captured also. So this basically it's missing for whatever reason. It could be a real packet loss or it's just not captured. Okay, so it wasn't captured, so now we get the duplicate ACK, like we do. And in the duplicate ACK, we can see that there is a option block with a sub edge. So you can see here this acknowledgement number is 813361, and this one is higher, so we know we have a gap between the ACK number and the left edge. Okay? So if the sender keeps sending, this right edge should increase, as you can see. So I do it again. This is the first block, or the first SACK edge block. So if I click on the next acknowledgement, there has more data been received after the gap. So the right edge, I don't know what to look at, this one, will increase because more data has been received after the gap. So the block that is telling the sender is, I got this also. So let's click on it, and you see it increases. And it will increase again for every packet that gets in, until there's either another packet loss, and you will get a second block or if the retransmission comes in and the blocks are removed, because then everything is whole again and the ACK number will just jump to the end of the full block. Okay, so basically what you're doing is like a kid playing with your toys, like the blocks and the pyramids that you put into a box, and as soon as you put it in, it's okay. Yeah, so if everything is whole and everything is there, you don't need the SACK edges anymore. You only need them while something is still missing. Okay, let's go down a bit. There's a couple of them, 29, 30, 31, 32. So we got into this one. Now we have missing stuff from that number, 813361 to 814821. Now we get the retransmission, and if that retransmission is the only thing that was missing, we already know which sequence number it must have and how long it is, right? So we can check it should have the sequence number 813361, which it does, and the next sequence number is 814821, and that should be the left edge of the other block here, as it is. So you can tell this is exactly the one thing missing from our transmission, and it fits perfectly. So after that you get the acknowledgement for everything. Like, everything is complete, thank you, acknowledge, done. So if we continue, we will see that once again there's packet loss, and there's another packet loss here. So now we will get two edge blocks, the second edges and edge blocks. So it tells me like I got one thing, then there's something missing, then I got another thing, and there's something missing, and I got the rest. So now we have to fill two holes. Yeah? So that's what happens all the time. You have to put in the retransmissions to plug the holes. So here's one, there's the other, and then the acknowledge usually at some point gets down to just one ACK block, SACK block. There it is. The retransmission was complete. There was a large piece missing this time. As you can tell, we get a fast retransmission. This one, fast retransmission, out of order, out of order, out of order. Those are basically parts that are also retransmitted, but only the first one is labeled retransmission. The out of orders are also retransmissions, so to speak. They're labeled as out of orders for some reason, which is something we have to fix, because they should be, in my opinion, be labeled like retransmission. And when we got all of them, then the hole is plugged, and there's nothing missing anymore. So we get the acknowledges at some point where only one SACK block is left. And when that is retransmitted, we're done again and have no SACK edges, right? So far, so good. That is pretty simple. You should already know this, unfortunately. This is just like, I'm repeating myself to get you up to speed, because now it gets a little more crazy. Okay? Everybody understood that? Who did? If you didn't, come and see me at the reef later, okay? I will repeat it for you as long as I have to. And if Hans ain't there, he will help me. Yes?
Blocks can you have?
How many blocks can you have? Excellent question. Does anybody know how many SACK edges you can have? Christian is saying 4. Carsten is saying 4. These are the German guys I came with. How many are you saying? Jim is saying 4 too. So we have 3 times 4, and nobody is arguing with that. Somebody said 5. Who said 5? You said 5? 5 or more?
Yeah, 3 or 4.
3 or 4. Okay.
Depending on timestamps.
Depending on timestamps, yes. 5? Okay, what does it depend on? Betty? It's 3 depending on timestamps. Actually, yes and no. We can basically agree to this. As long as you have space in your options, and they're quite size limited, you can have 60 bytes of options in the TCP packet, because the bits in the TCP header telling how long the options are go up to 60 bytes. So if there's anything in the TCP options that is taking away bytes from the remaining space that you can use for SACK blocks, you have more or less. Usually we go up to 4, unless you have timestamps, because timestamps, they take a lot of room. But as you will see, there is a lot of more TCP options coming in the future, and it may even happen that you can't fit all the SACK blocks into a packet anymore that you want to get in there. So you need to send an additional one. I will talk about TCP Multipath shortly in this talk probably. And in that case, you have options that are crazy long, and then you can put as many SACK blocks in a packet as you used to, so you need to send an additional packet just signaling the SACK edges. Okay, so the correct answer for most of my questions usually is, it depends. The problem also is you can use it depends as an answer to me only if you can tell me on what it depends. So if you say it depends, I will ask you on what. And if you don't know, you shouldn't use it depends, okay? Okay, so that was simple. Let's try something else. Who knows what a DSACK is? Yeah, Christian. You don't have to, I know that you know. A DSACK is a duplicate selective acknowledgement. And the funny thing about this is I have to answer this quite regularly on the ask.wireshark.org page, because people are coming up like, I've read the RFCs about SACK, but this doesn't make any sense. And then I'm saying, yeah, read the next RFC, and then it will make sense because this is something new. It's not SACK, it's DSACK, duplicate SACK. And you can see that the SACK block is not after the ACK number anymore, it's before that. What does it mean? It means that the receiver got a packet that it already had, and he wants to signal to the sender like, hey, dude, I already got this. Don't send it. It's a duplicate. I don't need it. Okay? It's like a signaling for, I got this already. Stop sending old stuff. So DSACK is a mechanism to improve the sending quality by telling the sender like, hey, I don't know what you're doing, but stop sending the old stuff that I already have. And I can show you a trace. Actually, that is one that I got sent by somebody asking about this. He was like, this can be SACK, it's wrong. And it's a duplicate SACK trace. So what you can see here is 3 retransmissions. This one is the first retransmission. We check which packet it retransmitted, sequence number 1. So this is sequence number 1. This is a retransmission to packet number 1. We have both of them, the original and the retransmission. So we know, yes, it was already there, and it probably got acknowledged too. Not probably, it got acknowledged too. Okay, answer question? Okay. So now we see a loopback here, and that loopback has a SACK for exactly the retransmission. Basically, like, there's the original, we've seen it. There's the retransmission, we've seen it, and this is the complaint about it. Like, hey, dude, don't send this, I got this. Okay? So if you see a SACK where the number of the edges is lower than the acknowledgement number, you got a duplicate SACK, not a SACK. So this is not something missing. This is basically like an information that the sender is doing something that is not necessary. So on your criticality report that you're turning in, this is like a footnote, basically. Like, oh, we have a situation where somebody's sending stuff that has already been sent, so this is not the optimal way of doing this, but this is not packet loss. This is not a problem in a way that, well, something got lost and stops me and slows things down. It's just saying, well, this was unnecessary. Okay, got it? So if you got the power of the DSACK and you know what it is, you can impress a lot of people, because as soon as they learn SACK, they will be impressed that this is possible and not a bug. Okay? So you upgrade your level just now. Good. And for the fun of it, I have this another picture to look at. So tell me, is this a DSACK or a SACK? And it's a trick question. And you can't use it depends. Okay? Huh? Yeah, sure. I don't have to, but I can. So, DSACK or not? Who says this is a DSACK? Okay, who says it is not a DSACK? Who has no clue at all? Maybe it's like right. Okay, everybody's still wondering what it is? Answer? Any idea?
I would say it's might be went out, or it's off by 1 billion, or whatever that number is.
Okay, that is a good clue. It's off by 1 billion. Okay? So now, what does that mean? Off by 1 billion. I mean, take a look at the window size. Is that even close to the window size anywhere? You know, window size is the space that you're able to receive, and basically this is somewhere else. It's like in the next universe.
Went out devices do this.
Really? It looks kind of very broken. This is not even close to being good TCP. So, I don't know what this is, but I know it's not correct. Okay, so I only got the screenshot. I don't have the trace because somebody said, I have a DSACK, but it doesn't make any sense. I think it's broken or something. What we suspect at the moment is that there's some kind of device between two nodes talking to each other that doesn't exactly know how this works and randomizes sequence numbers, but forgets about the FAC edges. So they get like, okay? The problem with advanced TCP or the SAC stuff is you have security devices that do sequence number randomization. And then the vendor stops implementing stuff and they don't do the TCP options. So they don't care about those. Or even, maybe they do, but somebody left the device running for 12 years because he can't shut it down, he doesn't want to, so it's still doing the old stuff and destroying the packets. Yes?
I've seen this before on the firewall where the handling of steps was disabled. So
Okay.
it was just passing the filter.
Okay, you've seen it on the firewall, the handling of sex was disabled.
Yeah, and it was randomizing the sequence.
It's randomized sequence number, but the SAC blocks in the options stay untouched. So we have like craziness. Okay, so if you see this, this is basically like a problem indicator in itself. If you see this on your network, find the device that is messing with the sequence numbers. Because you need to fix it. Either kick it out, or get a new one, or patch it. Because this is breaking stuff. Okay, it's hard to find, because you need to, like, okay, this can't even be, I mean, it's like Hans said, it's in billions away from anything that is possible. So, no, this is not the correct one. Okay, so it's probably just a normal SAC, but it gets distorted, so it looks like a DSACK, and I don't think it is. Okay, but it's hard to tell. I mean, I would have to have, this is basically a situation where I would start capturing at both ends to see what the one is sending, what the other one is getting, to compare it, and then say, well, there's a device in the middle that is basically messing with stuff. So if you see something like this, you need to get your 2 tabs and your 2 capture devices and travel to 2 locations at the same time unless you have a second guy. Okay? Yeah.
I'm trying to think of the problem that this guy has to solve. Is this trying to solve the problem of apps not getting back to the sender? The apps?
Yeah, maybe. The question was, is DSACK trying to solve the problem that acknowledgements may not be getting back to the sender, so the sender is retransmitting stuff because it thinks that lost? Yes, maybe. It's basically like an additional information to help the sending stack to adjust itself. But the question, of course, is why would a DSACK get through if the X get lost? Because X are so small, they should be the ones getting through the easiest.
And SACs sort of already solve the problem of what needs to be
Yeah.
retransmitted, right?
So DSACK is basically an add-on option that is just a helper. It's not a problem solver, it's a helper. Okay? Alright, so what else do we have? Now, I was zoomed, so I need to go back. Okay, duplicate X and the elephants. Who knows what an elephant is? long fat network. Those really long ones with a lot of bandwidth, and that's the one where we started calculating bandwidth delay products, window sizes, this kind of thing. So I've got another question for you. Assume you have a network set up like this. 10 gig, 1 gig, 1 gig, LTE, 150 megabit. What's the maximum throughput we can achieve with this setup? Somebody's saying it depends. Let's say the latency is like a 2-digit millisecond number. 20, 50, something. You have everything you need. You can scale up to placements. The max is the smallest stop. Is it? Really? In theory, it is.
Well, you need the round trip time.
Well, let me just guess a round trip time like 30 milliseconds.
And it's 150 megabit with packet overhead.
Yeah?
But so that's theoretical maximum because that's the smallest pipe. But if you do the bandwidth delay product and multiply by 2, typically, try to saturate that bit.
Okay, so Ansang is saying the theoretical maximum is 150 megabit, which is correct. So I didn't put theoretical in the question because everybody thinks theoretical is what I get. You don't. Okay? Christian and I were solving a problem like this for a company that has been looking at this for month and month and month with a ton of network engineers, and they couldn't find out what the problem was. Basically what they did was testing equipment, and they got 12 megabits on the end. 12 megabit, like less than a tenth of what was possible. And they were like, we don't understand this because 10 gig, 1 gig, okay, that's a problem, but that only means that we have packets coming in very fast. Then there's a tenth of that, but it's still way enough to fill up the LTE link, so what's happening? And I show you. So. And then this. I don't know if you can see it. Christian found it in the museum down there. Ack. So let's take a look at the bug thing. It's also called, as you can see. And it will take a long time because it's about a gigabyte. It's to T-Shark, so you don't have the bar there, you have to go here. And you have to go to here. So we have some time, so if you want to drink something or... It needs to get faster, but I can't do anything. I've got an SSD in this, and it's still not... Well, okay, I need to load it, and it's it takes a while. By the way, you can see that I've been at the previous SharkFest because I got a SharkFest 214 profile here. So, yeah.
Why is the source before the destination?
Why is the source before the destination?
Shouldn't you always have the old sniffer destination?
No, I always had the source before the destination, but I had the time to the right.
All time to the right, yeah.
But I get bad feedback from people like you if I do that, so my time goes to the left. Okay?
I did a quick difference, I was like,
Jasper,
Yeah.
what sort of problems do you see these days when you have asymmetric switching like the
Exactly that what I'm loading right now. This is what will happen to you. Okay, and I will tell you why. But first we look at it and we will try to get the it depends out of the way, and then we'll see what the problem is. It's so slow. Maybe I need to do this on the...
Jasper, repeat that question.
Sure. The question was, is this something that we see in the networks today if you have like speeds that go from 10 to 1 and even further down? So yeah, this is the problem that you will see. Sometimes. It depends on something, and I'll tell you on what it depends. Yes?
You said that we can get these files from your logger, your Twitter, and try to look at your way to copy it via Central.
Really?
Yeah.
You can't find it?
No.
Okay. Let me quickly. I try to find it for you. Not so fast, please. I think the loading process is slowing everything down. Let's see how far we are. Almost done. I will give it to you. Okay. Good, we got it. Okay. By the way, this is probably the longest file I've ever pushed through trace wrangler to an underminer. It was like crunching on it for more than an hour. So it took a long time. And I used the feature to replace strings in there, as you can see, because this was actually valid blocking before. So, lots of data. FTP, which is, as we all probably know, one of the best overhead to data ratio. So it's nice. Because I don't like synthetic tests, somebody does with NetIO and whatever it is. This is much better usually. So I could scroll a long time. What I will do is I will go for tcp.analysis.duplicate let's say greater than 100. Now it's crunching again, as you can see at the bottom. But it seems to be faster than loading. Okay, this also explains why I don't do network analysis on a laptop like this, because I need faster machines and more screens. So, here we got DSACKs. This is DSACK number 101. Can you see? 2, 3, 15, 200, 300, 400, still taking bets, 500, 6, 7, 8, 9. Will we get a 4-digit number? Yes, we will. Oh. DSACK number 1111. Okay, I can tell you that there's even higher numbers in there. It goes up to 1,100 and something. So, what's happening? I need to clear the filter again. And then we'll see something very interesting, because the DSACKs, usually when you see DSACKs, you see a retransmission and everything is fine, right? Okay. That will be a little surprising. As soon as this thing does what it should. The QT Shark, by the way, is not optimized right now, so it's slower, but the projects asked me to use it because if you are able to spot if an analyzer is doing something wrong, which means you must be pretty proficient with network analysis to be able to tell that Wireshark is showing something that is not correct, that is the most valuable feedback those guys can get, because you can tell them this is not correct, you need to fix it. So I try to use it as much as I can, so if I break it on stage, that's the best thing, because everybody will have seen what the problem was, and we can all do a back report. So if you think you're good enough to use Wireshark and spot problems that it has when decoding, please do, because that's the best feedback those guys can get. Okay? So they can only improve stuff when they know what's broken. They're not network analysts. Alright? So there's the DSACK, and guess what? No retransmission. But it looks like everything's fine, right? I can scroll for quite some time and everything's good. No problems anymore. So where's the retransmission? Let's find it. Let's see how long it takes. So what am I looking for? I'm looking for a retransmission that has the sequence number of this one here. So I go and say copy value, no, copy as filter. And then I do not a filtering, because filtering will, as you can see, always read the whole file and it takes forever. So I do a find, which is the button up here, and I'll push my thing, my copy values in here, but I'm not looking for a sequence, for an ACK number, I'm looking for a sequence number. So I go for TCP sequence, like this. Okay, this is just a find. And let's see if I can do a successful find. It's searching. This is an easy talk, I don't have to do anything. Just wait. Yeah, but it's close to the million packets, so we need to be. Okay. There it is, retransmission. Okay. So I did I filter? I didn't want to filter. Oh, my bad. Do the filter again because I want to see everything. This is what I do. I find something, and if I did a filter and I select the packet, I clear the filter again. The focus will stay on the packet that you selected, so you can look what happens around it. It's just taking forever, unfortunately. This is something that is quite much faster than the old Wireshark. But it makes no sense to improve code in speed until you got all the workings correct. So there it is. Whoa. Can you see? Do back 1, 2, 3, 4, fast retransmission. So if you were wondering why isn't it doing a fast retransmission, well, it is. But why do I have like 1,111 duplex following this one? Can anybody tell me why this is happening? What you see is like packet loss, do back, fast retransmission, do back, like the little ant, like I want to say act one more time, or like 1,000 one more times.
At least one of those apps are probably taking forever to get out of there in the first place.
The answer in front, which is quite correct, was the retransmission takes a long time to get where it should be, to the receiver. Why is that? So let's take a look back at the diagram. What happens here is this. We have a time gate up here, and this server is like, okay, let's send some data. Basically, it's not sending some data, it's sending a lot of data. This slams into this poor little guy, and this one has to break it down from 10 to 1, which means if it goes too fast, it's buffering. For how long?
Depends on the size of the buffer.
This is like a tsunami. Yeah, that's like a gigabyte coming in at high speed, and he has to break it down 10 to 1. So he's buffering. And the switches, in this case, they have a 100K byte buffer. Good luck with that. So it fills up pretty fast. And what does it do when the buffer is full and still more packets coming? It drops like crazy because there's no room. So you need to think of this like this is a bucket that is constantly being poured like half a swimming pool into it, and everything is like lost. But there's constantly more stuff coming in, so even if you push something out onto the link, there's already new packets coming in that fill up the slot and the space. So 10 to 1, and another almost 10 to 8 kind of thing. Same story on this end. Again, you drop like crazy, even if it's only a tenth of what was originally planned. So what will happen? Well, the receiver will get some packet loss, or it will notice that there's something missing, like we just saw, and then it will say, hey, do back, please retransmit. The duplex travel back, and he's retransmitting right away because my capture was taken at the server. So you see it go out right away, like, okay, I need to retransmit it, okay. And then, from what we see in the trace, we still get loopbacks like crazy coming back, which means it hasn't arrived yet, it hasn't arrived yet, it hasn't arrived yet for 1,000 and more times. And that is because this is completely separated still, so the retransmission has to get in line, it has to, well, basically get in line at the end. And everything in front of it has to get through first before it can. And if you're in really bad luck, and this is why it drops down to 12 megabits, the retransmission could be one of the packets that gets dropped again. So it needs to be retransmitted again, and again, and again. And that way, you go down from 10 gig to 12 megabits. The question is now, why is the sender sending that crazy amount of data? Why is it? Because it's allowed to, as you said, it's allowed to because of the TCP window size. Alright, what's the TCP window size in this one? How can we tell? We have the data connection starting somewhere here. SYNAC, and the one receiving it is the 01. So this one is saying, well, my window size is this, and it uses scaling, I think. Multiplied by 128. So if we take a look at what it's saying, we see it's advertising a window size of very, very nice 4 megabytes. Like, hey, come on, give me everything you got. And the server's like, okay. And he slams the infrastructure, basically like crazy. So now, why would a client go with a window size like this?
That way out of the box.
Because this was an LTE device which was pretty new, and the driver programmer thought it would be a good idea to put a hard-coded 4 megabyte window size in the driver. It's not, okay? So we told the guys, like, and remember, they were looking at this for a long, long time, like months. They couldn't figure out what was happening. And Chris and I, we did this in like 2 hours because we've seen it before. If you see loopback chains that go into crazy amounts of, well, numbers, and you see that somebody is sending a large window size and it gets filled up, and then you see packet drops, this is what will happen. And it's quite a good, well, pattern that you can recognize.
We saw the same kind of thing one time and got a hold of the manufacturer, and the manufacturer said, well, that's okay because the sender will go ahead and see that it's getting pushed back and start throttling things back and not send as much.
And no, it will not slow down if you're not really, really lucky and got a kind of very intelligent machine.
They will just keep going.
Most will just keep going, and especially that is true for most of the SAN and S storage devices I've seen. So if you got like a storage device in a computer center that is like asked to send tons of data, it will. It's like, okay, let's see what happens. Do it. And this happens. Okay, so if you have links that are not the same speed, and you have a receiver that has a window size that is just too big, this will happen. So a question, and then we will start starting. If you have a Windows 7 PC, will it advertise that size? This was a Windows 7 PC, but the LTE driver was overriding the window size. You have no chance with that card. You didn't. And so the operating system, we tried everything, like tell them, hey, do scale factor or something, disable it completely. It was completely ignored because the driver just said, well, I can do 4 megabyte. Yeah, so you have no chance to get that without the help of the developers correcting the driver.
So it's always advertising the 4 megabytes.
Always.
Whatever happens.
Yeah, always.
The sender be dropping its congestion.
Shouldn't the sender be dropping its congestion window? That's basically what you were asking, like shouldn't the sender go and slow down? Maybe it should, but most stacks don't. They're like, hey, this guy's telling me window size 4 max because if he's seeing packet loss, he should reduce it. He doesn't, so let's keep going. That's the problem. And you're right. We have a lot of discussion about shouldn't be the X frequency and the packet loss ratio be modulating the setting speed. These days, not yet. They still like, okay, let's do this. The window size is my only kind of fraud that I'm accepting, so they keep sending stuff.
Okay. You hardwire that attribute in the driver to get around any. Is that a possibility of manipulating that size in the
Well, basically what those guys did, I think, was putting the 10 gig switch on that port where the server was connected down to a gig. So they're forcing it down to a lesser speed, and that solved the problem. But in the end, the only real solution, if we're honest, is that the damn developers need to read RFCs, right? It's like this. Yeah.
Furthermore, could you argue that it's not the receiver's fault, it's the sender's fault, the IP drop situation?
The receiver is advertising the window, not the sender.
He's advertising the TCP advertiser injection window, which is non-observable. It's just for the sender.
Yeah.
So I would assert that it's the sender's fault, not the receiver.
Okay. He's saying it's the problem that the congestion window should be adjusted on the sending side, so not pushing out that much data if it's a problem like this. Yeah. So yeah, you could argue about this, but still, I mean, the driver should not advertise the window if it sees that there's packet loss. It should reduce it. That's what a normal Windows 7 PC does. If you're having packet loss, it will reduce the window size to slow the transmission down to a level where you don't have packet loss. Yeah, so yeah, we can argue about that for quite a long time, but in the end, I think the developers need to trust the TCP stack of the operating system to be doing its job and not hardcode anything into the drivers, which is kind of crazy because if you think that you have more experience in coding TCP stacks than the guys from Linux, Microsoft, and whoever, you should be doing this because it means that you're probably, well, thinking that you're too good. Okay. Yeah. It's really hard to hear you.
You think it was Bufferbloat? Basically, the buffer was waiting for
This is Bufferbloat, yes. So Bufferbloat means that you're overloading the buffers of the devices in the path because of the window size that is too big.
Okay, but also the buffer is on the device might be too big.
Yeah, but
It should not absorb that much.
yeah, but the client has no problem of reserving 4 megabytes of memory. That is nothing that the system will not be able to do. So on the receiving end, he's saying like, I only got one connection, I can do 4 megabytes, no problem. Okay, so well, I think the problem here is that the developer thought this is going to be used in the field where nobody is being able to push like a 10 gig link down to the LTE device, which is correct in most situations. But this means that the test setup they had didn't work. Alright? So I have no idea how much time I've left. Yes? Yeah, it's on the server.
So if the server saw over 1,000 different tracks,
We were talking about this yesterday, at some point, the sending stack must be like, hey, I already sent this, I still get loopbacks like crazy, that guy is probably nuts. Yeah, so, it must be something like this. I've got 10 minutes left? Really? Oh, okay. Okay, I've got so much more stuff. So close. Okay, I will make it. So, if you want to discuss this more, come to the reef and we will have a chat about it. It's probably better to get things done here. Okay, so I want you to notice this kind of pattern. It's what we will see more and more if this network speeds get higher and higher and the networks are not at the same speed on every link, and they won't be. You will have 10 gig cores, 40 gig cores, 100 gig cores, and you're going down to lesser speeds on the edge. So this can happen to you at any given time if the right things go wrong. Okay, so this is what it depends on. The window size and the speeds the differences and the large amount of data going out. If that happens, this happens. Okay, so we can close the really big one. Now, TCP fast open. That is something new. Who has seen TCP fast open? Nobody? Alexis, yeah, you do because you coded into Wireshark. Yeah. All right. So let's take a look at fast open. Basically, what it does is it tries to save time by putting data into the SYN packet. It's like I'm talking to Hansang and saying, well, by the way, I would like to talk to you and I want this from you in one packet. So you don't have to do like, hello, I'm Jasper, hello, I'm Hansang, okay, we're agreeing that we're both talking to each other, by the way, I want this. So this is like, I'm Jasper, I want this. Okay? The problem with that is, if you're allowing something like this to happen, I could go to Hansang and tell him like, hey, I want this, and I want this, and I want this, and I want this. Which is a security problem because I could just flood him with requests that are not good. So SYN flooding on another level. Because I could pour data in it, and that floods you much more quickly and basically fills up the pipe really fast. So what we do, or what is done to prevent this, is something called fast open cookies, which means I'm talking to Hansang, and I'm telling him, by the way, next time I talk to you, I want to use the give me something right away. And then he says, well, if you do that, here's the special number that you have to include in your request, and I know that it's you actually, because he wants to talk to me. Okay, so that's fast open cookie is something that needs to be changed first, and every connection afterwards can do the fast open stuff when it includes the cookie. And Hansang will know, oh, this is the number that I gave to Jasper, so it's okay, I will answer it. Because the problem we have with SYN floods is that the people flood you with requests from forged IP addresses and they never answer back. As soon as I answer back, they know it's the correct node, so we have sort of like an agreement and it works better. So this is what fast open does. So let's take a look at that. By the way, right now this is, if you want to try this yourself, you need to use Chrome, and you need to use a server that does this. So browsing with Chrome on Google, and tap it, and you have it. Okay. So what you see here is, and it's actually quite funny. Why does it say? Guys, I do have developers in the room. Can you spot the error? I see a hex file playing out there, and it's not turned on. Uh-oh. Well, it's not a big problem. Not a problem. So we do it like So what we see here is a SYN, and in the SYN, you will see something that you probably haven't seen before. It's saying TCP option experimental. And then you can open it, and it says this is a fast open cookie request. Yeah, they're trying things out at TCP sometimes, and if they do, they're not giving them option numbers. They just tell them, hey, use the experimental one, and then the number of, well, the kind thing here, that means what it is, and then you know it's a fast open cookie. So this is the first contact, and it says, well, this time I'm not using fast open, but I would like to next time. Then the answer comes back, and it tells me, well, this is your fast open cookie here. See? It's like a random number that nobody should be able to predict. Yes? Are firewalls following this one, if you're lucky? Right now, I would doubt it. So if they're, I don't know if your firewalls are messing with the layer 4, but if they are, they probably will drop this. And then you have basically no fast open happening. It will be the normal communication, which is not breaking anything, it's just not as fast as it could be. Good, so the next SYN will have fast open. Can you see the next SYN? Where is it? Which one? Give me a number. 18. 18. Why? Because it's green, right? Color coding is good if you do it right, not crazy stuff. So what you can see here is, yes, this is a SYN. Down here we have a fast open cookie, and it's right away doing the secure socket layer handshake. Like, By the way, hello, and this is my secret stuff. Putting all of it into the SYN packet right away to get it out of the way. The problem here is that if you're looking for SYNs in your Wireshark packet list and you don't have color codes like this, you will not find this. You'll think like, oh, this is the same communication link. Okay, so it can get a little confusing. So maybe you even want to do a color code for fast open happening, so that you can see, oh, this is a SYN with fast open. I didn't do this yet, it's just a normal green one for me. But this is what fast open is doing, and you can see that this is basically a SYN with data in it, SYN-ACK, and then the rest is going like normal. But you're just reducing the whole thing of one IRTT, one round-trip time shaved off.
So if you send packet 18 at this point, and it includes the SYN, packet 19 is the SYN-ACK.
Yeah.
So you're always going to do a SYN-ACK to the SYN, even
Yeah.
if it's buried in the load, correct?
Yeah.
So you could at least filter on the SYN-ACK.
Yeah, you could, but I mean, very often you don't have a filter going and you want to see where the SYNs are.
Yeah.
And filtering on SYN-ACK is not so much fun. Usually. For me, I almost never do. How much time do I have? None, right? 15 minutes? Okay. Rest of the day, really? I don't think the next speaker will agree, or if he doesn't like to do his talk, maybe he will.
It's lunch.
It's lunch, okay. Do you need lunch? Just kidding, yes, you need lunch. Okay. Good, so the next thing, and that's the final one, and I will only go into this briefly because it is just a bit too much right now. Yeah. If you use Chrome and go to like google.com, searching for something, it should use fast open. Maybe you even need to use like a Ubuntu or something that has this already included, because I think Microsoft is not doing it yet. I think the experimental stuff usually happens in the Linux stacks. So I think for this one, I use the Ubuntu 14 something. Okay. So Microsoft, please go ahead, do it. Those guys, they always suffer when they're here because I know them. Alright, so Multipath TCP. We'll see Multipath TCP. Because Multipath TCP is the biggest nightmare we are going to face, except for encryption when we're doing network analysis. And why is that? We'll see Multipath TCP here. Nobody? Okay, let's think of this. I have let's say a tablet PC that has a Wi-Fi connection and a mobile connection, like to an LTE network. And I'm at my home, and both are on, both are connected. I have both IP addresses going on each. And I'm talking to a server that also knows Multipath TCP. What the device will be doing, and the Apple iPhone users of you already have this for Siri, it will use both IPs for two TCP connections to the same destination host and spread the data across both links, both connections. So you will have packets in the one and other packets in the other communication, both going to the same server and basically using both IP addresses. The advantage of this is if you're leaving your home and you're leaving your network range of your Wi-Fi, your LTE connection will stay on and you just drop the second link, but the first link stays active and you will not lose your connection. If you walk into your office building and you have Wi-Fi again, the Wi-Fi will pick up, get a new IP address, add the new IP address to the TCP session that you have, connect to the same server, and you're on two links at the same time again. So you can do roaming with this. But the problem is, your packets will be, of course, put into all the channels that you got, and you can do more than two if you want to. So if you're analyzing anything, you need to look at all the TCP connections that are part of the same multipath channel. Good luck with that. Okay, so I think we need a new tab into the conversation statistics at some point where we're not looking at single TCP connections, but on the combined things happening in the TCP connections that are part of one multipath TCP connection. So the challenge is get this done, and what they do is they have data segments with options in the TCP options where an additional sequence number is used that is unique across all the communication packets belonging to the same multipath connection. Because every TCP connection uses their own sequence numbers, but you need to recombine everything that is sent on the multiple connections to the correct data in the end, so you need an additional sequence number. And that is put into options. So I can show you trace, and that's the last thing I'm going to show you in this talk. Here you have a SYN packet again. Open it, options, multipath TCP capable. This means, hey, I want to talk to you, by the way, I know how this works. I know multipath TCP, so if you can do it too, we can use this. Basically, it's a handshake within the handshake packet. So the other one says, well, yeah, I can do it too. By the way, here's some encryption and sender key stuff, so we need to be sure that nobody is injecting something in our connection, so they use crypto to do that. And then the communication is going, and it opens another one and says, well, I want to join the connection with another one. Okay, so here a second IP is coming in. If I scroll back up, you'll see that this is coming from a second IP. The first one is from 66.104, the second one is from 66.103. There are both IPs on the same PC talking to one server, and he's just using both IPs to talk to the server. And now they're transferring data. Okay? And you can also do things like, hey, I know that this IP address that I'm currently using with you will be removed soon, so please remove it. So you can do add address commands, you can remove address commands and everything, all of this happening in the TCP option, which is why I said the SACK blocks may have not enough space in the packets, so you will need to send an additional ACK just for the SACK edges. That can also be happening. Yes? Louder? Yeah, you can do that. The question is, I don't have it in here, but there can be packets that just say, there's more IP addresses that I got that I could use, so that the other one knows that it could talk on those. Okay? So, and just as a last thing for you to maybe wonder about, I'm a security guy now. I read network packets like before, but I also do security. So there's an interesting talk that was happening on Black Hat a while ago, and somebody was using Multipath TCP on like 10 connections at the same time to spread a malicious payload over 10 channels to get it past an IDS-IPS device, and guess what? It worked. So the challenge here is, and it's called the neo-hapsis challenge, is to write code that is able to reconstruct the payload from all the channels into a correct binary, and they give the MD5 hash and challenge you to do it. So if you want to do it, go ahead. I will do this with Trash Render at some point, not right now because I have other things to do first, but this is something we will have to worry about in the future, so you should get a read on Multipath TCP, because if you're looking at single TCP connections and it's multipath, you will only see parts of what is happening. So this is basically a heads up for you.
Could you pull up the dissector and go down to the multipath field in the packet?
So this is a challenge one. I don't know what's in there. Like this.
So trying multipath TCP, that's the actual packet.
No, the kind multipath TCP is telling you which multipath TCP has one TCP option number, and all these sub-options have a kind. So this is a sub-option.
So if I wanted to filter by that, usually when you click on it, it shows you the filter at the bottom.
Yeah, you can do that. Just apply it as filter. It's TCP option kind equals 30. Alright, so I think I'm over my time limit, am I? Over 10 minutes. I still have 10 minutes. Okay.
Graph all of the connections on the throughput graph and watch it open all of them at once very quickly.
Probably.
If you open a trace for the first time, you're like, is this multipath? Could you just open that really quick and see in 10 seconds? Oh, it is.
Maybe, yes. I haven't tried it, but I wouldn't do it that way. I would probably go and have a color-coded filter that tells me this is a SYN, that is using Multipath TCP, so I need to be on the lookout. So I probably do a SYN like in a different color. That's easier than always looking, hey, the first thing I have to do is open this graph. Nobody's going to do it. Okay? So yeah, you probably could. I mean, if you want to get this captured, it's called, I think, the neo-hapsis channel. So let's see if I can find it for you. This one, this is the PDF. So, you can get the trace file at their site, take a look at it, so you have a sample for Multipath TCP. And if you're up for a challenge, try to reconstruct the binary that they have. Okay? I haven't done it yet, as I said. Good. Other questions? Yeah, comment? Okay, TCP fast open is disabled on Chrome in Mac. But you can enable it. Can you? No, you can't enable it. Okay. So we have to wait. So thank you. If there's no further questions, we're done.